Here we go again. This time we're going to call this isomers. And then the subtitle is going to be D, glucose, and L, glucose. And what that's all about. Okay. So an isomer is simply the same atoms arranged in a different way. The same atoms arranged in a different shape. It's called an isomer. And there can be many isomers for a particular group of atoms. Obviously, the smaller atoms may only have one or two different ways you can put them together. Some molecules, there's only one way they can go, and that's it. There's no such thing as an isomer of carbon dioxide. Because carbon dioxide, CO2, it's a certain shape all the time. But the bigger a molecule gets, the more options it has to twist and turn and bend. And you can get different arrangements. So bigger molecules could have several isomers. And so the example we're going to use is glucose. So we're going to talk about isomers of glucose. We'll use that as our starting point for talking about carbohydrate molecules in general. Okay, so very briefly, I'm going to show you two different ways to draw glucose. One is called the Fischer projection. So let's draw a picture of glucose, and we'll call it the Fischer projection with a C in it. Projections are basically just ways to draw molecules on paper in 2 dimensions, which give us at least some idea of the 3-dimensionality of it. So the Fischer projection is when we draw the molecule in its chain-like form. Okay, so I'll have to move down a bit for some space. Okay, so here is glucose in its chain form. There are 6 carbon atoms joined together. 6. And then we have a double bond O at this end and H. So we have essentially a carbonyl group, functional group at this end. Then we have OHs and Hs in a specific way. And the reason they're in this specific way is because, remember, Vesper theory, they're all pushing away from each other and trying to get as far apart as possible. The problem, of course, is that what we can't see in this projection is the in and out of the board directions. And so we're drawing these things as if they're flat, but these H's and OH's are actually pointing in and out of the board slightly, if you think about the 3D way that carbon bonds. On the bottom, we'll do a shortcut, CH2OH, which means that carbon has 2 H's and an OH group also stuck to it. So there is a picture of glucose in the Fischer projection. Now, the thing is, actually, I'll give you a second. Copy that. Go back, go back. Back. Okay, there it is, Fischer projection chain. Now, what I'm going to do, though, is I'm going to draw beside it in a different color a sort of mirror image of glucose. Okay? Now, to understand a mirror image, I want you just to take a minute and put your 2 hands out in front of your face like this. And if you look at your hands, they are clearly different. The thumb points in different directions, and the order of your fingers is reversed. That's why we call one our left and our right. Now, that's when you look at it this way. But if you flip one hand around, you could overlay it on your other hand, and all the fingers match up, and the thumb matches up. But there's something that's not quite right, and that's the palm and back orientation. So when you hold your hands sort of with one flipped, they do look very similar, don't they? But what you may not notice right away is the front and back orientation. The palm and back of your hand are reversed. So a mirror image is not the same as taking one thing and just looking at it from the back. If I look at my right hand from the back side and then turn around and look at the palm, it is still not the same as my left hand, because my left hand can only look like that if the back is facing. You see? So that means that it's not just the same as turning around and looking at it from the back. It's not the same. In other words, I cannot spin my hand and make it look exactly like the other hand. That's what makes a mirror image slightly different, right? And so that's what an isomer is. It's got a slightly different, there's Norton, sorry. It's got a slightly different orientation. And the only way you can recognize it on this projection is by remembering there's a front out of the board and back into the board direction that's not being shown. So if you were to draw this glucose molecule sort of reversed, something like this, 3, 4, 5, 6. The bottom part isn't so critical. We'll just put him in there. What you'll notice is that you can draw it so that the OHs are on the other side, just like your thumb. But to do this, you have to rearrange the molecule. You cannot turn the black molecule into the red molecule simply by turning it around. I've got to make sure I'm doing this right. I think so far so good. So this one would have the H on this side and the OH over there. I forgot an H right there. That looks good. You can't just spin the black one and make it look like the red one. It looks like you can on this projection because we're ignoring the in and out of the board perspective. If I flip that black one around, it won't match the red one on the in and out of the board projection. And so this is like a right and a left hand. Oh, I missed an H here, didn't I? Right there. Okay? And so we have names for these isomers. They're both the same number of atoms. They are both C6H12O6, if you count them all up. But they are different ways of building. So when glucose is formed by all these atoms jostling together, it can sometimes fall into place as D-glucose, which we call, that's this one. Whoops, come back. Don't do that. We call this one D, black. While I'm pressing black and it's jumping down. So let's try that again. I'm going to press the black. Now it's going to, okay. D-glucose, which stands for the right-hand side. This is the right-handed glucose, right? The prefix dextra. And then this one over here is called L-glucose, the left-handed version. So just like your hands, you can build fingers and thumbs together and make a right and a left hand that are not the same, no matter what. They can look similar if you twist them, they're not the same. Same way we can build two glucose molecules that are like a left and a right version. And the reason this is important is obviously because the different shape means they will react differently. D-glucose has a different kind of, slightly different chemistry than L-glucose. So if you're going to be burning a sugar for fuel, it's possible one sugar will be better able to be burned than another. Okay? Now that's the Fischer projection of these two isomers. Now I'm going to show you another way to look at them. And to do that, I'm going to draw this glucose again very quickly. So let's do this. Let's do D-glucose first. 4, 5, 6. Right? Put all the... No, well, what we're going to do is we're going to turn the Fischer projection into the other projection. Okay? So we're kind of doing the next step. I'm going to just erase that and make that a regular C here. 1, 2, 3, 4, 5, 6. So this is the bottom, our CH2OH, right, from before. And if we use the D-glucose, we'll have OH on this side, and another OH, right? And then we have an H. And then I think we have an OH. Yeah. And so then we have an H over here, OH on this side, H, H, and on the top we have our oxygen, hydrogen. Okay. Now this is difficult to show in drawing, and we had some difficulty actually doing it with the models, but I did figure it out after while you guys were on break. Essentially, all we're going to do here is show what happens. This molecule is long enough that it can twist and bend on itself. And so if the molecule bends around, this carbon up here can bend around, and it can interact with this carbon right here, this group. And when it does that, there's a bit of a shuffle of the atoms. Okay? The H's and O's sort of rearrange themselves around the carbons in a slightly different way, but they're all still there. But we don't lose anything in this process. And so what you end up with is a molecule. Let me put in green the carbon numbers. I'll also make a smaller line so that 1, 2, 3, 4, 5, 6. So carbon 1, which is near the functional carbonyl group, is going to reach down and bond up with carbon 5, carbon 1 and 5. Okay? So let's redraw the picture. I think that's what I was using. So now what happens is you get this picture. You get carbon, 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 carbon. Over here, you get an oxygen. I'll just put it in red because it's very easy to forget that's an O when people are doing these pictures and they're all like carbon, 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 carbon. Now there's 5 carbons there, and there's one sort of dangling off the top. This one dangling down is this bottom one here, right? That isn't part of the ring. 1, 2, 3, 4, 5 make the ring because 1 joins with 5, and 6 is still dangling at the top. So the numbers would be carbon 1, 2, 3, 4, 5, and 6. So that's how it's kind of joined together. And then, of course, we have the other bits and pieces. So on carbon 6, we still have the H2OH. So put that in there. Don't let those little green numbers get in the way of all the other numbers because they're just numbering the carbons, right? They're not part of the bonds. You'll notice that carbon 5, because carbon 5 needs 4 bonds, there's something missing. There's the little H that's going to be stuck on carbon 5, so we could put them maybe over here. It's hard to do the 3D here, isn't it? And then carbon 4 has an OH and an H. And so we can stick an OH and an H on there. And then carbon 3 has an OH and an H stuck on it. And carbon 2 has an OH and an H. And I'm drawing them sort of across from each other rather than on the same side because Vesper theory says they'll push away as far as they can, right? And so maybe this one here. But we're going to see that that's not actually the case in just a minute. So there's the molecule. And if I count it all up, I can count 1, 2, 3, 4, 5, 6 carbons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And 1, 2, 3, 4, 5, 6 O's. So I have not changed the C6 H12O6 chemical formula. All I've done is rearrange it in a ring structure. The ring structure is harder to depict. It's hard to see now what's on what side. With the Fischer projection, there's a definite right and left side, so we can see where the OHs go. But with this projection, or this picture I've drawn, it's hard to see the sides. In fact, when you turn it into a ring, instead of left and right, it becomes more a matter of what's going upwards and what's going downwards. So for ring projections, we use a different projection called the Haworth projection, just to give us some idea of the differences, like what would D-glucose and L-glucose look like in ring forms? How would we tell them apart? In the Fischer projection, we see there's more OHs on the right side, that's the right one. And there's more OHs on the left, that's the left one. But if we're doing this ring, how do you know which one is which? So the ring is designed to sort of give us some depth. So let's draw the little carbon. I'll draw a little bit bigger this time. Let's draw the hexagonal sort of outline first. Remember, there's an O in this corner. So what we want to do is we want to make this look like you're drawing a table, right? When I draw a table, if I look at it from the ceiling, it's a square like this, and I can't see the legs. When I draw it sideways, it looks like that, and I can't really see the surface of the table. But if I do a weird sort of 3D-ish kind of pretending thing, I can make it look like I can see the top of the table a little bit. So that's what we're going to do. We're going to turn the ring so that it's kind of looking like this. So it's sort of like the top of a table, and it's really going in and out of the board. But we want to be able to still see it a bit. And so to do that, we're going to use some shading on our bonds to give that impression. All right, we're going to, so what I'm going to do is change the thickness of this pen so it doesn't get too crazy. So we're going to use a very thick line up front here to show this bond. And then we're going to color that in. We're going to color that in black. Probably do it like this. Oh, look at that. There, nice thick line. The problem now is we have to go we have to make this look like it's the very front of the tabletop. Then we have to make a triangle shape here to make it look like it's going backwards into the board. And then we color that in. Let's do it the hard way because I don't want to screw it up. Like that, and like that. So the idea is it's supposed to look like these two carbons on the bottom are closer to you than the other two carbons which are set back into the board. Does that kind of make sense? And then we just draw the lines up here to show those ones further away. So that's sort of a depth perception trick to give us the look. And so now anything that's above the table, right? Let's go back to our table. Oops, erase. Go back to our table. Our 3D table. If I draw stuff up here, we would know that's above the table. And if I draw stuff down here, we would know it's below the table, right? So by the same token, anything that's sticking upwards will be above this table, this ring table, and anything sticking down will be below, okay? All right, so what we're going to do is we're going to draw a line up for the CH2OH. And then here, we'll put a line sort of up and a line down. Everything is up and down in this projection. There's no anglies. Nothing on the O, and then up and down, up and down. And we will write in here, we'll put the OH here, and the H up here. There would also be a little H on this guy. I think he's down. Here we need an OH up here, and an H down there. Here we'll put the H here, and the OH here. Then we'll put the OH here, and the H right there. Okay, so now we can see that some of the OHs are definitely going above, and some are going below. If you go back to the picture of glucose in the Fischer projection, you will see that there are 3 OHs on one side and 1 OH on the other, right? They're back here. In fact, that doesn't make sense if I don't show you. So let me go back here to our Fischer projection. There are 3 OHs on the right side and 1 OH on the left side. By the same token, we're just turning left and right into up and down. There are 3 OHs on the downside under the table, and there is 1 OH above the table. So this is our D-glucose picture, with 3 on one side and 1 on the other. It's possible to flip all those and produce the L-glucose in the Hawthorne projection as well. But before we do that, we're going to simplify the Hawthorne projection a little bit. What we're going to do is we're going to say, you know what, organic chemistry is all about carbon, and everything is carbon, and there's just too many carbons to keep drawing. So what we're going to do is we're going to pretend that any time 2 lines meet in the corner, there's automatically a carbon there. So we don't have to put C's. So what we're going to do is take this picture and sort of redraw it like this. We're going to just draw okay? The top lines. Now I have to put the O because it's not a carbon. So I have to put the O in. And then I'm going to put this line down here, making a hexagon. And then I'm going to use the Hawthorne style projection on the bottom three lines. And I'm going to make this sort of a thicker line, like a triangle, like that. Color it in. And the same over here. Make it color it in like a triangle, like that. And then I'll join up the front really thick, like that. And there's my 3D tabletop. Now, each of these corners is a carbon atom, but we don't write C. We just assume there's a carbon atom in that space. And then we draw little up and down ticks at each corner to sort of finish off the picture. So you see, without the C's, it's a little bit simpler. We just have to know they're there. The other thing is, if there's nothing there and there should be, it's a hydrogen. So we can not write the hydrogens. We can write in here C, H2OH. Now, when you do this, you'll notice where I put the C. Don't write it like this. Don't write it like this. It's a subtle difference. Don't just be haphazard about it and write CH2OH up here. Because this line is stuck to one of those atoms, isn't it? And it's stuck to the C. The bond is with the C. So you should always write it so that the C is right on the line. And then you can put your H2OH over here. Went to my thick pen again. And then if we go around for our picture, if we look back at our picture that we drew before, all we really need to do is look where the OHs are. One on the top and three on the bottom. And the one on the top is here. So we'll write OH here. We'll put the OH here. And again, it's the O that is stuck to the carbon, right? And the H. So put the O on the line and put the H on either side. Doesn't matter which side. Typically, if it's over here, we put it on this side. But if your picture is squishy and you can't put it there, you can put it on the other side. So put the O on the line and put the H there. O on the line, H beside it. O on the line, H beside it. And we don't even have to draw the H's. All the other empty sticks, if there's nothing on there, we just assume it's a hydrogen. If there was something on there that was different, we would draw it. So this is the simplified version of glucose in the Hawthorne projection, where we try to use up and down instead of left and right for this ring structure. And of course, if we were to draw two versions, in fact, instead of drawing, let's be really cool here, and let's go to the internet, and let's put in Hawthorne projection glucose, and we should be able to get a nice picture that we can look at of the two glucoses, D and L. This one does the trick. Nope, that's a very poorly drawn picture. It's actually incorrect. I don't like that because it's got some weird business on it. Well, not really. It's just not as good as, here's the one. Nope. Here we go. Let's do this one. If you look at this picture, it should be very close to the one that we have. But you'll notice it's got a little beta on it. I don't want that picture because we're not ready for that yet. So I need to find something called alpha D glucose, which I will find. For some reason, it should be there. All right. Why don't I just write alpha? All right, here we go. Here is the picture that we drew. So what you can see here are the two projections. We have the Fischer projection on this side, and we have the Haworth projection on this side. And I think that looks pretty much like ours. The only difference is they didn't put the little upward ticks where the H's were, like I did. I like to put them there to remind me they're there. So on our picture, we had extended these lines like this. So there, now it looks like ours, right? And you'll notice the positions of the OHs, I think, are the same as the one we just drew. And that, of course, is called D-glucose. Don't worry about this weird thing here. We're just going to call it D-glucose. Okay? L-glucose would be the reverse of that. So I'll show you L-glucose really quickly before we lose our time. L-glucose. Enough to get it. Images. Oh, here's the two of them side by side, sort of. This one's better. Oh, this is the one I just had. No. Why am I getting all the... Oh, that's just the old writing on the board. Okay. Don't go anywhere. Just a second. 2 seconds. 2 seconds. No. Well, suffice to say that the L-glucose would have the OHs on the opposite sides. That's all. And so we'll summarize that when we do our next video. We'll take off from this point on, and we'll go from there and continue from that spot.